This is just a quick additional video relating to the design of the logic comparator that I'm designing, and this has been prompted by a very good comment on the previous video, and it relates to the use of DIL switches on the daughter boards, the module boards. So these are the boards that your test device would sit in. Now, I mentioned in the previous video that I had considered using DIL switches on these module boards, but decided against it. But I didn't really go into a lot of detail as to why I decided against that. I'm trying to keep the videos at this point relatively simple, so I'm not going into a huge amount of detail on certain design aspects, but I will cover them in detail in later videos. What I tend to do when I design something is go through the entire design as a white paper exercise, so that I have the entire design kind of fleshed out, even down to some fairly fine detail. And that's what I've done here. I'm just presenting it in bits and pieces to try and make it more enjoyable and not too tedious for anyone watching the videos. But in response to the question or the comment, I thought I'd just clarify a few points. Now, the first one is relating to why these boards are needed at all. Why can't you just plug the test device directly into a ZIF socket or something like that? And while you could use a ZIF socket, you would then need to incorporate the DIL switches onto the test unit itself. The reason for that is it most easily explained if I just do a quick sketch of a standard gate and then explain how that would be tested by the test unit. So if we take a simple 3-pin gate, then obviously it's got 3 pins, 2 inputs, 1 output, and on the test unit itself that means we'd use 3 comparators. So these are not the standard comparators you'd use in analog circuits, these are digital comparators. This is the circuit I showed on the breadboard in the first video. And so what you want to do is have your 3 LEDs. The LEDs would be on the outputs, and in this case we'd be monitoring 3 pins. Each comparator has 2 inputs. Now, 1 input would come from our reference, so if we want to test a device like this, we'd need a reference device, and so we would feed one of each of these 3 pins into one of the inputs of the comparators. Now, because we need to drive this device with the same signals we're getting from the unit under test, while we need to connect all the pins through to the respective inputs of the comparators, so for example these pins would all be connected like this, and that means that this pin would come to here, and then this one would come to here, and of course that means this one would come to here. But we also need to make sure that we're properly driving these, so we would need to connect this pin to here and this pin to here. That's to make sure that any signals, bear in mind this is on your unit under test board, so any signals being used to drive this are also being used to drive this. We can't connect the outputs together because obviously we'd be kind of defeating the point of the test unit if we did that. And so what we're doing is driving the inputs of our test reference device in the same way that we are with the unit under test device. In theory, these outputs will always be correct because they're being driven by the same inputs, but this is the one we'd be interested in here to make sure that when the 2 inputs on this device and this device are obviously the same, when they change, the 2 outputs should change in the same way, and if they don't, that's when this comparator would be triggered. So we need some way to create these connections, and that's what the jumpers are for on these small boards. Essentially what you do is you specify which are inputs by shorting particular jumpers. Now you could do that with DIL switches. In other words, you'd have a switch here, and then you'd have another switch here. So you would open that switch and close these two. And it makes it very convenient because you can configure and reconfigure these very easily rather than soldering jumpers. The problem is, of course, that if you were to put DIL switches down the side, firstly you would have 40 of them, and secondly you'd have to move the LEDs further away from the device, and it would make it far less clear as to which pin we're talking about when there's an error. And that was the idea of having quite a narrow slot, is that the LEDs are very close to the pins on the device. But as I said, I've gone through this design in quite some detail, and there will be two versions of these boards. There will be the version that I've kind of already implied would exist, and that's the ones where all the pins are used, and then you just short out which ones you use. And these could be used either for small devices or for 40-pin devices, whichever you prefer, if you want fixed configurations. You could actually still have flexibility in here, because a lot of logic devices have common pinouts, so you could just swap these boards and the test device based on the particular unit you want to test. You probably need 7 or 8 of these in total. But I've also got a second version of this designed. I actually got these designed already. These were the first things that I did. And they do vary slightly in that instead of having links all the way down, the bottom half has 2 sets of DIL switches. They'd normally be 10-way. I've got some 10-way ones ordered, but they're not here yet. But imagine if these were 10-way DIL switches. Then you'd put your device, anything up to a 20-pin device, in the top half of the module, and the bottom half will have these switches, and they would just relate to the individual pins. So this switch would be for this pin, this switch for this pin, this switch for this pin, etc. The only downside with doing this is the pinouts for the power would have to be pre-configured, so you'd still need one of these for each device based on their power requirement. So in other words, if you were to have DIL switches for power, you'd need a second set, which is why it's not really practical to use DIL switches in this format here, because you'd need a second row of DIL switches, and you'd end up with 80 DIL switches on every single module, which would obviously be crazy, and then the LEDs would be so far away from them devices to make it almost unusable. So the best middle ground is to have 2 sets of DIL switches in the bottom half. It will limit you to using 20-pin devices, but it would at least give you the flexibility to use these switches to set up your device, and then you wouldn't need anywhere near as many of these. Most logic devices have fairly common power pinouts, so it wouldn't be a huge problem, but you would need a different one of these to cater for ICs that had different power pinouts. So as I said, this is the idea. In a future one there may be other options, such as a microcontroller configuring all this based on a device selection. It really comes down to how much interest is generated by this. If only 2 people want it, then there'd be no point in putting that amount of effort into it. But if they are popular and people demand it, then it will be quite easy to add that to a later version. But for now, what I want is a version that is flexible enough to be used sensibly. That is, it's not going to be too cumbersome to use, it's not going to be too expensive to use, but will give us the flexibility that most people, I think, will be looking for. But without becoming impractical in terms of, okay, it's fine for certain users who don't mind configuring the modules each time they want to use them, but for me, having to mess about with 80 DIL switches, bear in mind that if you flip the wrong power DIL switch, you blow up your UET, then that's not something I'd really want to be using on my bench. It might be what some people use, and there's nothing wrong with that, but it's not really what I want for this particular test unit. So please keep the feedback coming, it's very useful, and I'll explain more about the unit and how it's going to work and the design as each video comes out and as I progress through developing the unit.